All right, section 9-6 is looking at momentum and kinetic energy in collisions. We're at last making it to our collisions. So these are the types of collisions which we got an introduction to in lab with some analogy. The elastic collisions are where the total kinetic energy is unchanged. It's conserved. And it's a useful approximation for common situations, though in real collisions, some energy is always going to be transferred. So you could visualize an elastic collision with a hard steel ball on a steel surface. And if you drop it, it would bounce right and return right up to that same height. That even though it bounced on the ground, it didn't lose any kinetic energy in that bounce. Inelastic collision is our sort of everyday collision where some energy is transferred. This is pretty standard. If you have a basketball and you drop it, it won't bounce quite up to where your hands were, right? If you just let it go. So this is the most common one. Elastic collisions, our first case. The problem will have to specify that it's an elastic collision. Otherwise, you have to assume it's inelastic because most collisions are going to be inelastic. Then within inelastic collisions, we have completely inelastic collisions where the objects stick together. This is the greatest loss of kinetic energy. So kinetic energy is definitely not conserved. And with our basketball example would be if you deflated your basketball and dropped it, it's not going to bounce back at all. But it could also just be two cars crash together and then they slide together as one object. So for one dimension, if it's an inelastic collision, this is our most general equation that momentum is conserved. The total initial momentum, m1 v1I, right, the momentum of cart 1 initially, plus the momentum of object 2 initially, have to be equal to the total final momentum of both individual objects, right? Where here's a depiction of each of the masses, m1, m2, and their initial velocities before the collision. Then there's an after picture. Usually with collision problems, you want to draw both pictures, before and after, because both are very important. And so then they label the final velocities v1, f, v2, f. And I put an extra box around this equation because anytime you have two objects that collide with each other, this equation is probably relevant. It's our most general way to state the conservation of momentum. After this equation, you can get into some special cases. Like right below it, there's a special case that you look for a completely inelastic collision with a target at rest. So target at rest means that body 2 is initially not moving. V2I is set to 0, so that disappears from this equation. Also, because it's completely inelastic, then after the two objects collide, they travel together at the same final velocity. So instead of calling it v1f, v2f, we just call it v, and they both have that same velocity. So this is a simplification or a special case scenario for the orange boxed equation above. Interestingly, the center of mass velocity remains unchanged during collisions like this. So we could calculate the center of mass velocity vcom with the total momentum divided by the total mass, where the total momentum is the momentum of one object initially plus the momentum of the other object initially, again divided by the total mass. And we could see this at play in this freeze frames of an inelastic, completely inelastic collision showing the center of mass velocity in pink here. So I'm going to make this a little bigger. There we go. So we have a scenario where we have a projectile coming in, v1I, towards a stationary target. v2I is equal to 0. The center of mass velocity is the location of the center of mass, where it looks like m2 is a little bit bigger. And it's an average, right, of the two velocities as well as that position. And you notice as the projectile comes closer and closer, the center of mass velocity also moves closer and closer to that target until the collision happens, right? And at the moment of the collision, the final velocity, v, is just equal to the center of mass velocity. The two of them travel together in that same direction. So the center of mass velocity, as time passes, has a steady rate. It is not changed. So there's a look at how collisions can play a role. We'll get into our specific case of elastic collisions coming up pretty soon. But for now, we'll take a pause.